if I have a polynomial x to the power n, where n is a natural number, what's the symbol for the integers? Z, that's right.
Wait. What?
Yeah, one moment. I'm fixing all my formatting because I've never used this computer before. It's not default yet.
To write a paper about math, and he makes me download stuff so I can do that. And I can just do that instead.
Yeah, I never used LaTeX. I didn't even write my dissertation in LaTeX. I wrote my dissertation in Microsoft Word because I didn't want to bother learning LaTeX. And it's way easier to do everything in Word. Like, okay, so what I just typed out was x caret n, like that. And you hit the space bar. It does the thing for you. And then comma, space, space gives you a big space. N greater than or equal to 0, comma, space, space. N, that's important. This little backslash thing, I don't know, that's a backslash, right? N backslash, and then I'm going to type in the word in. And then when I hit spacebar, it's going to turn it into the belongs to set symbol. And then if I want the double struck z as in integers, I'm going to type in backslash double z. And it's important to capitalize the z or you'll get a lowercase z. And whenever I hit enter, or sorry, when I hit spacebar, now it's a double struck z. So double z is the key for that. So if I have a polynomial, then we just calculate that with repeated multiplication. What's another common function? Exponents, right? If I have any exponent like a to the power x, where a is a positive real number, then I'm going to convert this to the natural exponent, which is saying that like a to the power x is going to be e raised to the power natural log of a, right? Because the exponent base e and the logarithm base e are inverse functions. And then there's a certain property of exponents that we're going to take advantage of, which is to say this is the same thing as e raised to the power natural log of a times x. So that I just need to be able to calculate two things. I have to be able to calculate a natural logarithm, and I have to be able to calculate e to the x. So if I can calculate the natural log of the base and multiply that times x, that's my new argument, and I plug that into the function e to the x. E to the x, I think, is probably best calculated using its Maclaurin series. Oh, yeah. Ben, are you watching?
Yeah.
Backslash sum underscore open parentheses k equals 0 close parentheses caret plus backslash infty space. And then you type 1 divided by k factorial f caret open parentheses k close parentheses to get the kth derivative at 0. Wait, what is the kth derivative at 0? It's e to the x. It's e to the 0. It's 1. Wait. That's the derivative. I also need x to the k. Yeah, there we go. That's my Maclaurin series. So if I ever need to calculate e to the x, I'm just going to use the Maclaurin series. I'm going to add up terms from my Maclaurin series until I get the desired level of error tolerance I want. Once the terms shrink so that they're small enough, I'll stop adding up terms. I'll take whatever truncated sum, whatever truncated partial sum I want for my e to the x calculation. The other thing is natural log. We can calculate natural log using the integral from 1 to x of 1 over t dt. Because natural log is the antiderivative of 1 over x. And if I try to plug in natural log of 1, I should get 0. A logarithm of 1 is 0, so setting the lower bound to 1 and the upper bound to 1 would give me a 0, and that's how I choose my bounds. Then, using a quadrature rule, like Crenshaw-Curtis quadrature or Gauss-Legendre quadrature, to do the approximating of that integral. Because I can't solve that integral directly. If I took the antiderivative, I would just get natural log, and I'm back to where I started from. So how does the calculator actually work if I type in something like 3 to the power 7.482, right? What your calculator is doing is it says, okay, I've got an exponential function. My base is 3, and my exponent is 7.6215, right? A weird exponent. It does it in 3 steps. First, it calculates the natural log of 3, and then it multiplies natural log 3 times the power that you told it, or the exponent, that part. It does this multiplication, and then it feeds that multiplied product into the e to the x Maclaurin series, and it truncates the Maclaurin series at some point. And that's important because we've got to break it into little bite-sized chunks, because my calculator only knows how to add, subtract, multiply, and divide. To do more fancy stuff, like a to the x with my calculator, I've got to reframe that algorithm a to the x in terms of add, subtract, multiply, divide. The Maclaurin series is great because in the Maclaurin series, all you have to do is multiply x times x times x times x, divide by the factorials, and then add them together. So there's nothing crazy about that. And then quadrature rules, what you're doing is dividing 1 divided by your number, and then multiplying by a weight, and then adding all those together. So again, you're just dividing, you're multiplying, and you are adding up stuff. So that's the story for exponential functions. Okay? If I have a logarithm, like if I want to calculate a logarithm with some base a of x, this is the same thing as the natural log of x divided by the natural log of a. Do you guys know why that is? No? Okay, I'm looking at Becky's face and I'm getting a no. So, because in general, we have this. a logarithm base a of x is equal to a logarithm base b. No, sorry. Logarithm base a of x. We'll say that. Can we agree on that?
Yeah.
All right.
We can leave it at that.
Did you see it?
Hold on. Okay. So what's the definition of a logarithm? The logarithm is the inverse function of an exponent. So if I compose the two, if I have an exponent base b composed with the logarithm base b, those cancel each other out, right? So I just get an x. Does everybody agree with the left-hand side here? I can replace x with b raised to the power logarithm base b of x. Okay, so then there's going to be a property of logarithms that says whenever I have a power inside my logarithm, I can take that outside of my logarithm, like this. So where the power of b is logarithm base b of x, I'm going to take that outside of my logarithm and multiply. One of those properties of logarithms you learned way back in college algebra. Yeah. And then the last step in all of this is I say, well, that means logarithm base b of x is equal to logarithm base a of x divided by logarithm base a of b. And so this kind of looks like what I have above, but now replace b with a and a with e. We get logarithm base a of x is equal to natural log of x and natural log of a. Right? And since I can calculate the natural logarithm by that integral formula, and then I can use quadrature rules on the integral to approximate the integral as to whatever accuracy I desire, now I can calculate a logarithm of any base by taking two of those natural log integral quadratures and then dividing. Which is, again, that's what we want because we want to be able to calculate stuff. And our computers can only do add, subtract, multiply, divide, so we've got to break it down into little bite-sized chunks so that they can eventually work it out. So we talked about, okay, what do you do with polynomials? What do you do with exponential functions? What do you do with logarithms? Then, what would we do with sine? One idea is just the Maclaurin series. Because sine of x has a Maclaurin series. I'm almost definitely going to mess this up, but we'll try. It's the sum k equals 0 to infinity of, it's the odds. It's going to be 2k plus 1, x to the power 2k plus 1. Is that right? Oh, factorial. There you go. Is that right? Because that skips over the even terms, and sine's an odd function, so it shouldn't have any odd powers of x in the power series. Oh yeah, I forgot about the alternating sign. See, I knew I had it wrong. Thank you, Sage. This is a adventure lecture because I haven't typed in my lecture notes. I don't have any. I've not a chance to proofread. But yeah, so definitely this is going to start with a positive x as the first term because sign's initially increasing around the origin. And then it will alternate positive, negative, positive, negative, positive, negative. So I think it should be -1 to the k where k starts at 0. Yeah. Okay, good. Another idea, and I'm not sure if it would work, but maybe, is what if I have x equals 2000? You know, the first few terms of the Maclaurin series are going to be relatively itty-bitty. So what could I do instead? I could take the modulus of x, specifically x mod 2 pi. Do you know what I mean by modulus? Yeah? Does anybody not know what I mean by modulus? It's like the remainder. You do the division algorithm and then you take the remainder. So like 15 mod 7 is 1 because you have 14 as the quotient and 1 as the remainder. So 15 mod 7 is 1. If I take 2000 mod 2 pi, it's going to subtract away all the multiples of 2 pi until I get down to just the x, and then I can plug it in the Maclaurin series. And that way I have to take fewer terms of the Maclaurin series to get to the relevant part. Because it moves my point where I'm evaluating it closer to the origin. I don't know if that's necessarily used in practice, because I don't know how much flops would be required to calculate the modulus of something. And maybe it's just one flop, right? Because divide is a flop. And when you divide, you automatically get the remainder. So maybe it's just one flop for the modulus, and maybe that makes a lot of sense. But in any case, that would scoot it closer to the origin, and then you do your Maclaurin series. So maybe that's the smart thing to do for big X, for X bigger than 2 pi. But that's an idea. And then the same thing, same for cosine. Cosine of X also has a nice Maclaurin series. And that would be kind of the same thing. I think it's just 2k factorial, because we're only dealing with evens when we talk about cosine. So if k is 0, then I get 1 over 1 times 1. First term is positive 1. Yeah, that makes sense. That's right. And then, again, take the modulus of x before the Maclaurin series. So we can get sine and cosine pretty easy. Okay, so now we've talked about what to do with polynomials, what to do with exponents, what to do with logarithms, what to do with sine, what to do with cosine. How would you calculate tangent? Yeah, I could calculate a tangent by just sine divided by cosine. How would I calculate a secant? 1 over cosine.
Oh, yeah.
Oh, yeah.
I was with you. I was lost.
How would I calculate a cosecant? How would I calculate a cotangent?
Cosine of sine.
Yeah. How could I calculate an arctangent? What?
The integral of whatever x squared plus 1.
Perfect.
Yeah.
Yeah, I could just say, I know arctangent of 0 is 0. And so let's make this the integral of 1 over t squared plus 1 dt. And that's nice because calculating 1 over t squared plus 1 is just a matter of multiplying, adding, and dividing. So I can do that with Clenshaw-Curtis quadrature or Gauss-Legendre quadrature. And we're in business. And likewise, I don't remember the rest of the formulas for the other inverse trig functions. But I think that's the deal. I think that's what you would do for the other inverse trig functions. Let me pull them up really quick. I'm a massive hypocrite because I force all my Calculus 1 students to memorize these, but I don't personally memorize them. I have my other tricks of remembering them when I end up on a desert island and I have to recreate math from scratch. But or if you ever find yourself in a time machine and you get transported back to the year 1500 and you want to, you miss the comfort of scrolling YouTube shorts on your smartphone and you need to recreate society, recreate civilization from scratch, How do you remember all this? Yeah, so notice each one of these could be figured out with a matter of multiplying and adding and dividing for the integrand. And then you could take an integral using some kind of quadrature rule to get back to your inverse trig function. The only thing that's a little bit tricky is the square roots, right? Like if I wanted specifically to get arcsine, it's 1 over square root 1 minus x squared. So what about arcsine? So arcsine of x would be the integral. I don't know what the lower bound would be. What's arc? No, it would be 0. Okay. Of 1 divided by square root 1 minus t squared dt. Yes. For the square root function, the square root of u is just u to the power 1/2, right? So treat it the same way we did a to the x. You're going to say this is square root of u is equal to e raised to the power 0.5 times the natural log of u. Now you know how to take the natural log. You know how to multiply that by 1/2. You know how to plug that into the Maclaurin series for e to the x. And then you've calculated your square root. And you do that every time you need to evaluate your integrand in the quadrature rule to get you the arcsine. So for all of the inverse trig functions where you have a square root, that's how you could treat the square root, treat it like an e to the x thing. What would I do if I didn't know the formula for arc cosine, but I'm like taking a test and I need to know the formula for arc cosine?
Ask the professor.
What if he just laughs at you? A maniacal laugh.
Looks like we're not getting points in that question.
You're welcome.
Start begging.
Arctan.
Yeah, so what I would say is, and specifically not the formula for arc cosine, but for the derivative of arc cosine. Well, I would say this. Cosine of arc cosine of x is what? X. Because the definition of arc cosine is that it should be the inverse function of cosine. And if I compose a function with its inverse, I should get back the identity function. So there we go. Cosine of arc cosine is equal to x. The next step would be to take the derivative of cosine of arc cosine of x. And this requires the derivative chain rule, but the chain rule says first we take the derivative of the outside function. So we take the derivative of the cosine. The derivative of cosine is negative sine, and we're going to leave the arc cosine alone. And then we multiply by the derivative of arc cosine, right? Let me make this look nicer. So I'm taking the derivative of both sides of the equation. What's the derivative of x with respect to x? 1. Make this look really nice. Here, this is a trick then. Instead of hitting the Enter key, like if I want to make a page break, I'm not going to hit Enter on my keyboard. I'm going to hit Shift and then Enter. And that's really important. So instead of Enter, Shift Enter. And if you hold Shift while you press Enter, and then you select these guys, right click, click Align at Equals, and then it'll align these equations at the equals sign. But it won't do that unless you hit Shift Enter. If you just hit the Enter key, it won't let you align at the equals. So you got to do the Shift Enter thing. But all right, so now I know that the derivative with respect to x of arc cosine of x is equal to -1 divided by what? Sine of arc cosine of x. But this doesn't look like the formula we are used to seeing. How do I show that sine of arc cosine of x is really just the square root of something, something, something? Ooh. Gotta draw a picture. And my picture involves this nice right triangle here. This is my angle theta. This is my right angle from my right triangle. Cosine is the opposite over hypotenuse, right? And so for opposite over hypotenuse, I want x divided by 1. That way I can write cosine of theta is equal to x divided by 1. And that way I can write theta is equal to arc cosine of x divided by 1, right? That's how my inverse functions work. Now, if theta is equal to arc cosine of x divided by 1, theta is equal to arc cosine of x, what I really need to know is what is sine of theta?
Wait, isn't sine x over 1?
Oh, you're right. Sorry. Cosine is adjacent over hypotenuse. Thank you. Now that I want sine of theta, I need the opposite over hypotenuse. So I need this side, and what's this side length? What's the opposite side length? That is not what I wanted. I've got to use my
1 minus x squared.
Pythagorean theorem to find that this is square root of 1 minus x squared divided by 1. So that means sine of arc cosine of x, because sine of theta is arc cosine of x. Sine of arc cosine of x is square root of 1 minus x squared. And that's how I figured out that the derivative of arc cosine of x is -1 divided by the square root of 1 minus x squared. And that's why I'm unapologetic hypocrite. And I do not memorize the stuff that I tell my Calculus 1 kids to memorize, because I know that if I was forced into a time machine and I had to travel back to the year 1500 and I had to reinvent calculus, I probably could, because I could just think about it for a minute and recover stuff like this. Okay. What else do we have to talk about? In general, there's multiple strategies for calculating something. Number one, if it's a polynomial, you evaluate it directly, right? If it's a polynomial, then just do it. Number two, if it has a nice Maclaurin series, just calculate a truncated Maclaurin series. What if it doesn't? Well, if it has a nice derivative, you can use an integral quadrature of the derivative. For example, the natural log function has a nice derivative, 1 over x, and so we could do an integral quadrature of 1 over x to get the natural log function. Arctangent has a nice derivative, 1 over x squared plus 1, so if I want to calculate arctangent, I could use an integral quadrature of 1 over x squared plus 1. I'm trying to think of what other strategies. We can also solve nonlinear equations using like Newton's method. The bisection method, the secant method, etc. Like on your project 2, I gave you that as one of your strategies. It's like, if you really want to know what y is, where y is equal to natural log of x, what you could do is solve the equation e to the power y minus x equals 0. Right? X is a constant that somebody's giving you to calculate with because you want to know the natural log of x. Y is the unknown, and so you could use Newton's method on the function e to the y minus x until you find a 0 of the function e to the y minus x. And you can solve it like that. The fifth strategy, and this is maybe less common, but you could also say if it has a nice antiderivative, you can use a differential quadrature of the antiderivative. And this would happen almost never, right? Like all the functions we've talked about so far, all those like trig functions and whatnot, their antiderivative is not nicer than the function itself. Any analytic function you're familiar with, the antiderivative is not going to be more easy to calculate than the function itself. It's always the opposite. It's always that the derivatives could potentially be nicer, but in general, never the antiderivatives. The only examples I can think of where this might actually be true is like, what if you are a chemist and you're trying to come up with some research in thermodynamics? So like, suppose we want the specific heat capacity of some material. And if I perform this experiment at constant pressure, the symbol we use for the specific heat capacity of a material at constant pressure is a C with a little subscript P. Well, this is the derivative with respect to enthalpy of the temperature of the material. And so this is a case where you would say, I really want to know the specific heat capacity of my material. I can't measure that directly, right? Nobody makes a meter stick that measures specific heat capacity of a material. But they do make thermometers. And so what I could do is I could set up an experiment where I have like a furnace with a precisely measured, I don't know what you call it because I'm not a chemist, but maybe like a calorimeter or something that's measuring how much energy, how much heat energy we're putting into this vessel. How much energy are we putting into the furnace? So you know how much, I can't think of a better word to say. You know how much heat you're putting in. You can also measure the temperature of your material. How quickly is the temperature rising as I add the heat? And so temperature would be an example of an antiderivative of the specific heat capacity where we can actually measure the temperature. We can evaluate that function by just looking at what my thermometer reads. And so while we can't directly evaluate the specific heat capacity, what we could do is we could use a differential quadrature on the temperature as a function of heat. And it's a funny function because you don't even know what the temperature as a function of heat is. The way you're evaluating that function is by taking temperature measurements as your material heats up. But that's an example of some way you could use a differential quadrature of an antiderivative. That's something you might do in thermodynamics research.